Okay, we continue for the second part. Hello, back there again. So this is the last we left on the slide number 16, the cumulative distribution function of the weighting line scenario. So how to calculate the cumulative distribution function as far as time more than 1, right? It is the big function of time equal to 1 minus e to the power of negative lambda t, right? This is as if like 100 minus the rest, right? So that's why it is 1 minus to exponential negative power. Okay, equation number 2 we applies to this case study example. Say for example in a fast food restaurant, for example, McDonald's or KFC, they are interested in studying the arrival of customers. You know that restaurant must balance out between the peak hours with their load to their employees. For example, like a fast food restaurant like McDonald's, we would know that their peak customer arrival busy time is normally between like 11:45 until 2 o'clock, which is the lunch time, right? So as such, during the high load customer coming in, the arrivals is very high. So McDonald management need to disburse their employees more on the attending customers who are coming for lunch, for example. Perhaps less on supplementary work like checking inventory, control, for example, control food stock or uh, delivery. So most of their employees will be a load of the work shifted towards the counter or towards catering customer order, which is serving food. Okay, so lesser important job will be left, and most load will go to the food serving. Okay, and this fast food want to study the arrival of its customer, right? So during the busy lunch period, they have observed that an average of 20 customers arriving per hour. 20 customer, okay, basically big number of customer, 20 customer arrive per hour. Okay, so if it is 3 hours, there's going to be 60 customers, right? So 5 hours is going to be 100 customers. However, based on Poisson distribution, it is normally distributed arrival in terms of customer, right? So the fast food want to know if a customer has just entered the store, okay, for example at 12 noon exact, 12:00 minute. So customer arrive at the store, what is the probability of another arrival in 10 minutes, right? So one customer arrive at 12 exact noon, what would be the probability customer will enter by the time of 12:10 minutes, right? This is what the question says. So how to estimate that? So we use the previous formula, function for big time equal to 1 minus to exponent minus power of minus lambda t, right? So we use equation 2 with a lambda equal to 20 minutes over 1 hour, which is 20 over 60, which is 1/3 of arrival time per minute, because our focus is on the next 10 minutes inter-arrival time. So in order to calculate the probability of the next customer will arrive in the next 10 minutes, so function big T equal to 1 minus to the e to the power of negative lambda t equal to 1 minus e to the power of negative 1 over 3, which is 20 over 60, 1 over 3, okay, multiply by in the next 10 minutes, right? So your calculation will bring into the probability of 0.96. This means 96% of the chance that customer will come in the next 10 minutes by 12:10. 10 minutes in the afternoon. Okay, that is the how to calculate based on Poisson distribution method. Okay, this is what Poisson distribution is all about. It's all about all the normal curve, right? This distribution has a unique relationship to the exponential distribution. Exponential is something curved like this, which is Poisson distribution is the curving like this, right? So basically, this Poisson distribution is a discrete probability function in the form of this formula, okay, which is f to the number of 0, 1, 2, 3, which is the function of serial number, which is 0 customer, 1 customer, 2 customer, 3 customer, equal to the lambda multiplied by t to the power of n, and is basically number of customer arrival, right? E multiplied by E to the power of negative lambda t divided by n to the factorial. Okay, so normally in this kind of calculation you need to use a scientific formula calculator. For example, like this calculator, in order to execute the calculation. Okay, like a Casio scientific calculator. So by that you could calculate lambda equal to average arrival rate within a given time interval, okay, like 10 minutes, 5 minutes, and so on. T is the number of time periods of interest, normally t equal to 1, okay, and number of arrivals, okay, 0, 1, 2, and so on. Okay, E is an exponential. It is a natural logarithm of 2.178. Mean equal to lambda multiplied by t. Variance, right, is a lambda squared by t. Okay, this is the second case example we execute using Poisson distribution function. Okay, one fast food is interested to study in the arrival of a customer, because they can shift the loads, balance the loads between the employees and also the arriving customers. During the busy lunch period, they have observed an average of 20 customer arriving per hour based on normal Poisson distribution curve. So the question is, what is the probability of 2 customers arriving in the 5-minute window? Okay, what are the chances that 2 customers arrive within the 5 minutes time interval? So how to calculate this? Solution says that we use equation number 3, which is this formula, right, shown earlier. So f to the function of n is the number of arrival. So lambda multiplied by t to the power of n, exponential to the power of negative lambda multiplied by t divided by n factorial. So in order to calculate this, lambda is every 20 customers within 60 minutes. Right? So it means that 1/3 arrival per minute, because our focus is on the next 5 minutes time interval. So the calculation is basically this, right? 1/3 multiplied by 5 to the power of 2 multiplied by e to the exponent negative 1/3 multiplied by 5. So you will have the calculation as 0.26, which represent 26% of the probability of chances 2 customers, okay, 2 customers will arrive within the 5 minutes. So by this, you could predict that in the next 5 minutes, if 2 customers coming, it is only about 26%, or about 1/4. Okay, 1/4 of the time, 2 customers will arrive within the next 5 minutes. Okay, that's the way the calculation how we execute using equation formula number 3. Okay, let's take a look in the topic of variation in inter-arrival rates. All right. Inter-arrival rates in which, as a service provider, you must manage the balance between the how many customer coming and how many workforce is attending the uh, bulk of group customer arriving. For example, for like a call center, this is a call center data, right? So average call per hour, right? uh, 1, 2, 3 is a average call the call center receive within 1 hour. So based on the hour in which it is operating, like normally call center is operating 24 hours. Like this hour, 1 a.m., 3 a.m., 5 a.m., 7 a.m., 9 a.m., 11 a.m., and 13 p.m., 15 p.m. up to almost midnight. So it could be deduced that call center will receive the most number of call, for example, 2 call to 3 calls, right? So within hours of 1 o'clock, right? So up to the night time, right? Around 10 o'clock, right? So these are the most peak time, which is the call center will be super busy, attending customer calls for about 3 hours per hour, like around 7 o'clock or 8 o'clock, okay, which is at this peak, and this represent uh, 7 p.m. Okay. So if we take a look on the doctor or clinic that attending patient, check their patient. If you have 5 days a week for clinics, the doctor will have to attend patient the most during day one, which is normally Monday, Tuesday, okay, Wednesday, Thursday, and so on. So from Monday, right, percentage of arrival daily physician visits, about 120 patient arrive to be checked by doctors, and then gradually reduce up to week day number 4, Wednesday and Thursday, Friday slightly increase on Friday before the weekends, right? So these are the trends for arrival rates and the variation that they experience in comparison, like a call center, peak time around 7 p.m. Like for the doctor, for the clinics, health clinic, most doctor are super busy during early days of the week, which is Monday, right? Okay, now we compare the Poisson distribution and the exponential equivalence. Okay, if we take a look on this timeline, right? So Poisson distribution are measuring inter-arrivals of customer arriving within 1 hour interval. Okay, at this interval arrival, only one customer coming. At this inter-arrival interval time, two customer coming. At this third inter-arrival time, no customer coming, and so on. Right? This is more on Poisson distribution. It compares in between equal time length of arrival, how many arrive within that interval. However, for exponential distribution, it is observing on the time between arrival in minutes, right? Between arrivals, right? So this is arrival 1, and then it waits for another 62 minutes before there is another second arrival, and it waits another 40 minutes for the third arrival, and again next it will wait for the next 123 minutes for the fourth arrival of patient or customers. So these are the difference between Poisson. The timeline arrivals is divided equally, but for exponential equivalence inter-arrival times, customer is measured in between arrival of first customer to second customer, third customer, and fourth customer. And this is measured by the exponential distribution approach. Okay, for example, like this is a normal Poisson distribution of class mark grades, right? So, for example, this is one subject that display the grade distribution for student A plus, A minus, B plus, B minus, C plus, and so on. So we would see that the distribution of Poisson is like this, almost normal, in which normally highest at the peak at the center here, which is most student can score A plus and A minus and B plus, which is at the peak, and later moving to the right, lesser and lesser students score lower grades, right? And of course, not many students can attain or score A plus. Okay, so most nominal grade scored by student are A minus and B plus. This is the highlight or explanation for Poisson normal distribution. Okay, looking at the queue configuration of customer waiting to get their service, for example, like ATM, there are 4 ATMs, right? So these are basically single line, single server, all single line, single server for ATM, right? However, you can switch in between ATM's line if you see this waiting line become minimum, right? Of course, you could switch here if there are lesser number of people in comparison to your current line. That is ATM machine. For airline counter, for example, you want to check in your luggage, right? So there are 4 services representative of the airline, right, serving you. So customer must enter to this queue, and then you turn, go here and wait here, waiting until the next serving available counter to entertain customer check-in for their luggage. This is airline counter at the airport. And the C type is at hospital pharmacy, in which you are given I would say, a number. Okay, it is a serial number, right? You will be given a number, and you could sit here waiting and wait until the number being called. If you are number 5, and then your number is being called, and then you go to the front, you get your service and get your medication. So these are 3 types of normal queue configuration, like ATM machine likes, or airline counter like, or at hospital pharmacy like approach. Okay, let's take a look on the structure of the queue discipline. Okay, queue, which is line, or people who are taking turn to get service. It's a queue discipline. There are 2 approaches in seeing this, how it works. First is a static. It is approach of first come first serve rule. Who come first, they will get the service. Or in the discipline of dynamics, okay, you could see that either selection based on individual customer attributes like VIP or important customer, or for example, like business class in airline, or for example, the elderly and veterans, they select based on certain criteria so that they could serve them first, or selection based on status of queue, right? So this is special case, or this is based on status of queue. Okay, if the number of waiting customers are big, right? So then they will serve first, or selection based on status of queue, like a round robin approach, in which dentists will have few customers. They are all get treated at almost at the same time. Perhaps they have the dental customers. Perhaps these customers are all waiting to patch their tooth, right? And so 3 at the same time, dentists will treat them or will entertain them. Perhaps this is the cleaning, and perhaps this is a patching, and perhaps this is for grinding, right? So all will be served. So then dentists, upon patching, so the teeth, dentists need to uh, leave for a while, perhaps 10 or 15 minutes, to wait for the patch become hardened. And meantime, for that 10 minutes, dentist will go to the second patient in order to entertain or take care of their tooth problem. And also the third patient will be treated accordingly based on sequence who needs first. Okay. So as such, waiting time is becoming minimum for the dentist, so they could save some of the time, meantime, waiting for the treatment to get cured. So during the same time, rather than the dentist waiting, they could serve other customer meantime. Or it could be based on dynamic, but selection based on individual customer attributes, like based on priority, right? For example, elderly first, pregnant lady first to board the flight. Preemptive, like ambulance, they are given special right of way in order for the ambulance to arrive hospital as soon as possible. Or based on processing time of customer, right? So based on certain kind of formula rule, right? Constant multiplied by mu rule. Perhaps there are some sort of formula of timing so that they can get served. Okay, that is the explanation for Q discipline, few approach, static and dynamic, right? So outpatient service for customers waiting, you could see in the form of these three types. A types, like walk-in service time. This is A type. B type, it is appointment service, it is approached by seeing doctor by appointment. Okay, and type C, right, basically it is based on second service time approach. For example, you have to have a repeat visit to see doctors to get your service done. Okay. If you take a look on type A, based on walk-in service time, right? For example, this customer, total of 408 customer. So the average of waiting time is 9.61 minute. It's about less than 10 minutes for walk-in service, right? So service time per patient, doctor could deliver 7.48 minutes per patient, right? In comparison to type B, this is by appointment type approach. So in total, how many patient the doctor could see? It is 365 patient, which is slightly less compared to walk-in service. Average waiting time is 12 minutes, 74. Okay, average waiting time. And service time per patient 9.56 minutes. So if it is by appointment, right, even though you could doctor could see less number of patient, but they can spend more time with patient, listening to their problem, health, and get some feedback. Okay. However, for the type C, it is a second time service visit, which is a repetitive visit. So total number of patient they could see 134, right? Lesser time, the average waiting time is 6.5 minutes, and service per patient is about 5.45 minutes. So most service time is based on this approach, which is exponential approach, which is like this, right? This is exponential curve approach, right? This is also exponential, and this is quite exponential. Okay, these are the case of doctor meetings with their patient, doctor checkup. Queue in traffic light system. This is a general observation as far as a queue is concerned. In Malaysia, there are traffic light which is installed with a counter, right? 99, 98, okay, 97, 96, and so on. So they wait based on counter. So we are not sure whether this is the most efficient type to control the crossings of a junction, right? So, however, if this is with traffic light, it is much easier to control in terms of traffic flow. But how about if this junction is without traffic light? So which one serve first? Which one will pass through first, and which one need to wait, and which one is next? Okay, in Malaysia, if you could do some reflection, like if this is a junction, okay, and you want to turn to the right and no traffic light, so normally it is very hard for this car to turn right if there is no traffic light, because most of the vehicle who are from coming to the left goes to this way, they have the right of way. So this turned out to be kind of unfair, because if this car arrive first, right, they got to queue so long until all the left car from the left pass through to turn to this side. So in the USA, in this kind of junction, if there is no traffic light, so there is no such thing as that the car from left is got the right. So it is based on first come first serve. If this car comes to the junction first, so stop, and he or she will be passing first. So if the next car come to this junction and stop, and then they gonna have the first right to move later after this car. So this is what we call first come first serve in other developed country like the USA, but that practice is not implemented in Malaysia. Okay, in Malaysia, traffic from the left has the right of way. Okay, at some time we think that it's a bit unfair to have that kind of rule on the road, in comparison to first come first serve, first come make the turn or pass through first. Okay, some of the service facility arrangement as far as queuing, waiting line, and how the customer will get served, like parking lot. Well, it is basically self-service. You park where you would like, but normally parking lot people park at nearest point where they can go to the facility at the nearest distance. At cafeteria, so serve is in series, like first come first serve. Toll booth like this, plaza, toll plaza for payment. So basically, you got to take turn in queue or in parallel. Okay, move next after your customer at the front get done. Supermarket, it is also based on self server arrangement, is self service or parallel servers. Okay, you can change queue. At hospital patients, right? Many service centers in parallel and series, not all used by each. So hospital is something like serve at a supermarket, in which could be parallel. You could switch line, right? So those are implemented for waiting lines in the facilities to get your service being served. Okay, guys and girls, it's about almost 30 minutes of my lecture for part 2. I would like to thank you for your attention in listening, following, and absorbing my lecture. So that's all for this time. We adjourn here. Thank you very much.